So, ladies and gentlemen, welcome to the 40th Fisher Memorial Lecture. These lectures are given to honour the memory of R.A. Fisher, who was a leading statistician and geneticist. But one of the key features of Fisher's work was his extraordinary geometrical insight, which he applied both to multivariate analysis and also for developing analysis of paleomagnetic data in support of the hypothesis of continental drift. So it was a very great pleasure for us in the Fisher Memorial Trust to be able to welcome as this year's lecture Kanti Mardia, Professor Kanti Mardia, who is known for his particular geometric insight. So a worthy person to explain to us this particular aspect of Fisher's work. I'll just give you a few remarks about Professor Mardia himself. So he's received many prestigious honours, in particular the Guy Medal in silver, and also the Wilkes Medal of the American Statistical Society. And his work has indeed been involved with directional data and with multivariate analysis. But he's not just a theoretician. His work has also been applied in medicine, in genetics, and so forth. So it's a very great pleasure for us to welcome this year Professor Kanti Mardia to deliver our 40th Fisher Memorial Lecture.
First of all, let me say great excitement to be invited to such a important phenomena. Fisher was a great phenomena, and to be part of it is something which I never thought I would be. So many thanks to Fisher Memorial Trust for inviting me, and also in particular to Stephen Sain and for the work which Brian Charlesworth, who kindly did a lot of things. They had so many emails. I was bombarding them with questions and more questions. So I thought I took the opportunity, as it has been already pointed out by Stephen, that geometry was one of the most strongest point of R.A. Fisher. But he was so wide that trying to pick a topic is so difficult. So I selected these two areas in which I've been working for years and years. I think the subject has moved so far. So multivariate analysis and statistics on manifold. So and beyond. So the way I will present the lecture would be first his legacy, historical, which I hope all can understand, I think, including myself. But then also there will be how it has moved forward beyond the time still, but that became in the root for all of us. So it has propagated in various ways in modern world. So I will move to the next. Let us see. So these are the contents, and you will see a color scheme. I think, I hope you allow me. So there would be 3 colors in hierarchical order. So when it is red, you wake up. I have to wake up as well. When it is bold, then it is important, but not essential. So if it is in ordinary font, then I think they are details, and you could just ignore it. So we will see how it works, actually. So as I said, I've taken 2 of his subjects so one is his fundamental paper on spherical distribution in 1953. But you will see that he was working long time before then. So it was a bit curious to find it is not 53 when it is published, because he was always motivated by some scientific example, illustrative. So I will give you some anecdotes related to it. Then the other is multivariate analysis. Of course, the subject is very wide, and foundation on discriminant analysis, which has changed its character. Now it is more statistical learning and so on and so forth. But the heart is still, it is his. So, there is now there will be some concluding remarks. So Fisher in 1953 in picnic in Australia. So this person named Jeff Watson will be keep on coming. And he gifted this particular photo to me. He had various versions. This version he passed on to me, which was in a picnic taken in 1953. So now next. So this is something again for general audience. I am a great collector, and my colleagues, they know I keep on collecting things. And in particular, I have a very big collection of fingerprint. So in one of the collection, I found, of many statisticians' handprint. I don't think anyone here handprints are there. The full handprints of his family. So if you look, this is his family in 1945. So they are complete handprints, and also at that time, L.S. Penrose, father of great Roger Penrose, working on field called dermatoglyphic statistics. So there are all kind of measure they would take, like ATD angle and so on and so forth. So that Sarah Holt, she collected these. So she was research assistant to L.S. Penrose as well as Fisher. So, and there quite a lot written in the biography written by John Box. So topic 1, so how the foundation. So first I will give you background, what is this subject. Some of you wouldn't know, even they are statistician, because they think this is not a part of proper statistics. It is not mainstream. So I thought better alert everyone, and that how he tried to alert R.A. Fisher that this is a very important area. So big data, high dimensional data, and sparse data are all becoming new frontier of statistics. There is no need for me to remind. Changing technologies have created this flood and have led to a real hunger for new modeling strategy and data analysis. So the modeling have taken as a great frontiers now more and more with big data. Of course, is a different type of technology. So what is non-Euclidean? Actually, they are, or this statistics on manifold. So the manifold simple examples are, simplest example is circle, angles, which you must have come across somehow, somewhere, I hope. So in this even simple example, if you want to do average 1 degree and 359 degree, then you get 180 degree. And I hope you agree that 180 degree is the correct answer. Do you? It's wrong. Of course, intuitively it should be 0. It's on the other side. There are 1 degree 359 sitting on my right hand and 180 on the left hand. So even in this simple case, arithmetic mean you have to reinvent the concept, the geometry, the appropriate geometry for it. So it changes, it throws up many major challenges, both mathematical and statistical. So great care is needed. So in simple terms, statistical manifold deals with many things, non-Euclidean variables, mainly by underlying geometry, what has been mentioned. Example are circle, sphere, torus, shape space, and so forth. So I will give you little bit of flavor. I think don't want to grill too much. I think in 45 minutes. So what you have to remember that angles are points on a circle. I think that's the, if you remember, and that's the manifold. So the landmark paper in directional statistics is R.F. Fisher 1953 dispersion on a sphere, and appears with a motivating example, remnant magnetism data. I think he, in all the new paper what he wrote, he always have a very good motivating example which he was working with others, and I will give you more flavor of it later on. So so he write in his paper, I think just to convince the referees that this is a different type of statistics. So the statistics would have led to be developed the observation, if the observation discussion had in fact involved errors so large that actual topology had to be taken into account. So the like circle, you have to take, the circle is circle, unless you try to open it, then it's a different thing. So the question is, then he start, however entirely, is not however entirely academic, for there are in nature vector with such large natural dispersions. The remnant magnetism found in sedimentary rocks do show such considerable dispersion that an adequate theory for the combination of such observation is now needed. So I think he is talking to referee really. I think because they say, what's the problem? We have so much of statistics well defined. Why do you want all these extra efforts? So then he says, my examples are drawn from the very fine body of data on the remnant magnetism of isolending lava flows, historic and prehistoric, which were put at my disposal by Mr. Hosper. His name will come again. I think it is a very important event which took place and this paper came in existence. So he wrote his paper, and at that time, of course, people didn't believe in statistics of manifold or that it needed anything, so it didn't go too far. But however, Jeff Watson at Princeton University, some of you would know, late Jeff Watson, he received a copy who says in his conversation in statistical science, we sent a food parcel to his daughter, John, in England at his request, and as a thank you note, he sent me a reprint of his 1953 paper, which is not an easy reading. I think most of his work, of course, Fisher knew what he was talking about, but for a reader, I think it requires a real hard work. Even today, if you read that paper, there are so many things hidden. So anyhow, I had a look at it and suddenly saw that I could clarify things. And there is a more and more about it. So 56 to 70, I'm just giving you background how the evolution took place. Following Jeff Watson and Michael Stephen, another name, made several key contributions. I think they really took whole thing in their own hand. So in 1970, they were heydays, and partly I wrote my directional book in Hull actually, and now I'm back to Hull. 1975 more so with discussion paper which I had in Journal of the Royal Statistical Society, and they were all big brain of that time were the discussant. There was Kingman, there was a David Cox, there was David Kendall, and so on and so forth. So it really received attention which it needed, the subject. So then there was nothing happened much. I think people got fed up. They were looking for other things. But 2000 or so, a resurgence of interest led to new stride. And why? Because mainly through the recognition by applied people, image analysts and life scientists of importance. Jochen Hein is here, Charlotte is here. I think, that how bioinformatics depend, angles on torus on it. So I think Oxford is a good place for this particular area of life scientist. So this momentum now continues as some statistician, and I think I somehow others put that line, and you try to guess what it is. So what it says that some statisticians do regard this as a mainstream subject, but not all. I think it is still there is some feeling that it is a small area, niche area, and they can do without it. So when I wrote my book in 1972, and Edward Evan, who was with me at that time, who was kindly come to this lecture, that I created many names. I think not that all, and most of them are accepted now as a proper terminology. So von Mises, I will talk about, that is distribution on a circle, and the way Fisher went, he didn't care that von Mises circular is there. He went his own way to the whole p-dimensional work. So there is a Fisher for sphere he did. Then there is a higher dimensional sphere. Then what is called now von Mises Fisher distribution. Then there is some extension called Fisher-Bingham, and then there is on a rotation group, on orthogonal group, matrix Fisher. So Fisher is everywhere, I think, and it's nice that I could talk about him here. So first I will just give you a bit of mathematics. So the status of von Mises distribution on circle is same as the normal distribution on line, and I'm sure most of you are familiar with normal distribution on line. So, because it has got similar kind of structure, that it has got first exponential family, second it has got two parameters, it has got one like a mean and other like anti-variance, but it is concentration parameter. So in a reverse order, inverse variance, parameter kappa greater than 0. So, but you can see that normalizing constant is a Bessel function, is not an easy, so which has given headache to many people. With computers, of course, advancement, the headache is less, but even then, when you got a big data, it is important to try to correct it, and I will show you how. So the distribution is symmetrical with mode at mu equal to 0. So for kappa equal to 0, theta is uniformly distributed, just like in roulette wheel. If it is not biased, then roulette wheel is uniform. For large kappa, theta is normal with mean mu and variance 2 over kappa. So in other words, this is a philosophy which continues in this area, that when there is a concentration, then you have kind of a tangent projection. So in tangent projection, then you can do what people were doing previously, because there is less error. So you can do the linear statistics. So there is a little bit of, again, so the key thing in what I am saying is that there are two things. One is resultant R bar, and other is mean direction. And to focus on this x bar, which is the center of gravity. So if you take that angle between x-axis, that theta bar is the mean direction of this data point, and R bar is the resultant. So R bar is 0, then it is you have got uniform sample, R bar equal to 1 for highly concentrated, because you can't go beyond the circle, because R bar is less than 1. So MLE, nicely, that mean direction is theta bar. So it is a mean direction, just it is analogous, but again it involves MLE of kappa involves two Bessel function. So now Fisher strikes in 1953. So this von Mises has done in 1918, but as far as when he wrote his paper, he was not really aware, and he was so great that he has no way to go to all these things when the subject has not developed. So he created, so you polar coordinates, longitude, latitude, or that form of it, and then the distribution look horrible. It is there is a kappa, there is a mean, a pole, alpha, beta, but Fisher didn't put it this way. He was so clever that what he did was, in his paper, he didn't give that formula at all. He goes straight away rightly, because otherwise it would have been a headache for any reader. So took the North Pole as the mean direction. So if you take North Pole as the mean direction, then you have the simple form that it is theta has got this distribution and phi has got uniform on circle. So remember, theta is co-latitude and phi is longitude. So, and then this thing, it continues that, because eventually when there is a concentration data, it must mimic normal distribution. So it has got, again it becomes an isotropic normal with 0 mean and unit variance, and for kappa equal to 0 we have uniform distribution on the circle. So then the work progressed. I think Watson and many others came, why only to 1 and 2 dimension, go to higher dimensions. And you see that this is more simple now. I think what I gave you first was most complicated, so that you get bit excited that what to do with it. And then slight, and then this is further instead of e to the kappa cos theta mu tx, where mu is the mean direction and then kappa is it. And then there is this normalizing constant. So for p equal to 1 it is von Mises and p equal to 2 is Fisher. So you can study this in higher dimensions. So again the same thing, there is a mode at and mean direction mu, large concentration, it has got to isotropic normal, kappa equal to 0, we have the uniform distribution. So this thread continues, and that's is the driving in a way, that if it doesn't go to normal, then there is something wrong with your formulation of the model. So now I take you back to what I said, that in circle. So now think of what are the statistics now. When you've got a sample, what is the mean direction? When you've got sample, what is the resultant? And here this diagram gives you an idea, but also this MLE, it involves, I want to focus that it is a bit complicated when you have got high dimensional data. So this, it becomes much simpler in that particular notation, embedding in Euclidean space, that it becomes x bar has got this 2 r bar x bar 0, there is a mean direction and there is a resultant, and the same thing goes through, that x bar is the center of gravity, and for circle, it is simple to work with angles, which we understand more easily than going for directions. So that's a, so now estimation, you grind on, do MLE, and then you come across, this inversion. So mean direction is no problem, but when you come to this, you deal with a big Bessel function. But recently, myself and my colleague has introduced and used new method, score matching. So where simply the estimator becomes something cos theta sin square theta, there are no Bessel function, and you lose only moderate loss of efficiency. So if you are doing this over and over again, then from computational point of view, it makes sense. So now back to 1953 paper, why and when was the material written? So when I started writing this talk, I thought better I do some digging. And this digging, I went to, of course, the well-known biography by John Box. So Runcorn, Hosper was Runcorn's student, very famous name in remnant magnetism, who collected data. They were struck by the fact that these lavas group themselves into those along the present field and those opposite in a manner strongly suggesting a hypothesis. The direction of magnetization of Earth had been reversed at some period of his history. So that's what motivated him, that Runcorn explained this to Fisher and asked him how the particular statistical problem can be solved. Fisher pulling out some old notes he had made before 1930. So the thinking, because that was one of his, I think, great period, 1920 to 1930, Fisher made progress leap and bound. I think quite a key paper came. So Hosper quickly used the method, and there are three very important papers which laid the basis for paleomagnetism work in tertiary age. So that's something. So what is it? How he did it? I think what did Fisher do in the 1953? So he has Hosper data. This is one data I'm giving. There were more data there. N equal to 45. So he wanted to examine whether this mean direction has changed the sign. In other words, it has become plus, become minus. It is in the opposite direction, reversal. So the MLE, if you calculate for that data, it looks very near, is it not? If you don't know statistics, they are very close. But if you do a bit more, between mu and mu hat, MLE is 3.9 degree only. So using the Fisher distribution, it is found that H naught is accepted with very high probability. So that hypothesis what Runcorn, Hosper had, I think that's had led to the full answer. So kappa equal to 7.5, you can't do linear statistics. I think it will be lost. So linear will not be appropriate. Further details are given in Mardia and Jupp. So this is why I'm saying this Mardia and Jupp is because those are the books which have been inspired by R.A. Fisher work. That's why it's not a sale talk. It is just that how much he inspired. So he had two goals in his mind when he wrote. The goal one, to provide methodology for the analysis of more or less widely dispersed measurement of directions such as frequently arise in geology. So that was one. And then second was the nature of inductive inference. So he has had many examples, and he thought that this example will exhibit for Fisher distribution his ideas, fiducial ideas in a clear light. So about goal, my assessment must be wrong. The Fisher-von Mises distribution has become principal tool for analyzing spherical data. So goal one is definitely achieved, but goal two of non-standard example, which is Fisher distribution, has not received comparable attention. So the further assessment of this goal is required. I think there are many clever people, they could go into depth of this. So now topic two. So I am now moving from now known topic to the what was previously unknown topic. So it is something. So multivariate analysis. I'm sure C.R. Rao word most of you would have heard. I think I'm. You would have heard C.R. Rao. In statistics, you can't do without him, just like you can't do without R.A. Fisher. Was one of Fisher's PhD student. So in a paper in 1964 in biometrics, he wrote Sir Ronald Elmer Fisher, the architect of multivariate analysis, summarized the pioneering work of Fisher in multivariate. So these are the quotes. So how much was known in field of multivariate analysis by way of theory or application before Fisher did his pioneering research? So not much was known. So many important contributions by others have also been inspired by this work, including my work, his work, and the various books. He has forged a number of important tools and demonstrated their use in applied research, especially we know in the field of biology, all of which are bound to stay on the books and be used continuously. I think so. This is a good summary by him, and then he ends. Truly, he was the architect of multivariate analysis. So there are two areas I have taken, in both of which he has made such an impact. I think so. His legacy, I think, is so great. So modern computational advances have given many extension of Fisher work. We will deal with only one aspect, because you could spend hours and hours, going through his distribution theory and many others in discriminant analysis and its extension to classification trees and statistical learning. So that's again another landmark paper. This is 1936, and I'm sure that 1953 was not really 1953, the previous paper. It was much before. The use of multiple measurements in taxonomic problem. So the data which is plant related plant taxonomy, iris data, this has been used in most of multivariate book in S+, and you will see that this is a very good example, and why I will tell you. Perhaps you will learn first time, those who have been using this. So in his collected, he wrote about his view of it in collected papers. So in between 1930 and 1940, he published 4 papers, one after another, on discriminant analysis. In the first 90, he introduced and applied the linear discriminant function, LDF. Also considered the problem of classification. In one paper, how much is there? Mind-boggling in the 1936 paper. He also connected the problem with the regression analysis, introducing the dummy variables, which I won't be able to go through. So Fisher 1936-1930 paper, his legacy, dealt mostly with the result needed for the comparison 3 species. So I will have a word S equal to through illustrated on the now celebrated iris data. The question posed by Fisher, mathematical, very good. What linear function of the 4 characters, because there were 4 variables, will maximize the ratio of the difference between the specific means to the standard deviation within a species? Very well formulated, and you can do the mathematics now, perhaps. I will show you, give you some hint. His 1938 paper, then I think at that time community was very strong. There was a work in USA by Hotling, in India by Mahalanobis, and all had the same strand. What he did was he reviewed and connected his work with what was going on and extended. The second half of this paper contains an attempt for S greater than or equal to 2, means more than 3 population. But the treatment was somewhat incomplete, but completed in his paper 39, 1940. And fortunately, he took opportunity to collected papers to write his notes, I think, which is a great thing to have. So this is the data, the celebrated iris data. So there are 3 species, so S equal to 3, and then there are 4 measurements, 4 variables. So the first 2 species, Setosa and versicolor, is very important, that they come from the same colony, but the third one, so there was some biological evolution problem. The third one was not from the same natural colony. So there was a question whether it is a hybrid of those first 2 or not. So one of the aim was to discriminate. So initially he set up the problem without any need of assuming any distribution. But then, as usual, he would be testing hypotheses without telling them testing hypothesis. So he will be calculating. So at one point he said, therefore, very important that at once conclude that if the measurement normally distributed. So he assumed this, and as it happened, I have introduced in 1970 how to test multinormality. It is called Mardia's, but that can be ignored. So what it does, that you have invariance, and the citation, I think this is one of the highest used paper in my other paper, which I think are much better quality and contents. But surprisingly, because of its uses, I think this is where the application runs a science. I think the statistics, with applications. So I introduce these measures which has got good properties. Obviously, that they become for p equal to 1 univariate case, they become the ordinary. They depend on the moment, third moment and fourth moment as required. The most important, the invariance, just like a scale and mean location invariance you see in those, that is invariant under affine transformation. So for normal case, this becomes equal to 0 and this becomes p plus 2. So there is as if we are not skew, and p times p plus 2. So p equal to 4, and I think this is important. So we have got p equal to, in particular example I will show you how it works. So under normality, you can have the asymptotic distribution, and these measures are available in all standard packages and now one of the most popular measure. So we come to this data. So p equal to n equal to 40, and what you concentrate is 3.1, 3.0, 3.2. So they are nearly 0, but unless you don't know statistics whether they are 0 or far from 0, the significance becomes important. And then kurtosis are very near normal 24 value. So you do this calculations, then you find first they are roughly in the same ballpark. Roughly, even if you didn't know statistics, didn't know test of significance, that it looks reasonable. But when you do the tests, they are not significant at the 5% level of significance. So Fisher's assumption for the iris data was really justified, and it is not. Now you will see this justification has got a more things which I will show you later. So the subject moved. I won't go through all this detail, but classification rule came out that if you have got a new x, new iris, then which one to give to first, second, or third. So it comes from his mathematics, which I will skip. But figure-wise, if you could see by a very large concentration that Setosa and versicolor are very near comparatively. Virginica is nearer than Setosa, but it is not a hybrid. The picture shows this canonical variate. So there is a overlap between those two, but it is not hybrid. So that's a. So now I come to classification region for iris data. So this now going legacy to beyond what's going on just now very quickly. So you have recall. So I will do dot, dark dot circle plus and delta for these three in that order 1, 2, 3. But for giving some hint graphically, in 2 dimension we can see easily. 4 dimension, I think is mind-boggling. I think the visualization is like time and space. I think it's the same thing. So recall that iris Setosa and iris were taken from the same colony, but the sample of third species differ from the two not being taken from the same natural colony. So I will just flick some slide. Fisher discriminant rule is a parametric method, because it depends on distribution. Partly it is a multivariate normal is driving force. But new now method more are more non-parametric. One is I will just give you a flavor of kernel classifier and classification tree classifier. So this linear discriminant, you will see Setosa, versicolor, virginica, they are well separated. They are 140 out of 150, so that it's a remarkable separation. because there is more overlap between versicolor and virginica. But otherwise, 140 proper classification is a good one, and one can calculate the error of this. So now, if you do kernel classifier, so you saw that these boundaries are linear, the line, but they allow curves, so they get a bit better, 139 out of 150 instead of 140. So, so then you go classification tree classifier, and it is horizontal and vertical division. So it gets 141 out of 150. So it is similar. And why it is similar? And this is where some conclusion on iris data. So we have applied 3 methods. We have given their classification rate. So there is a book, interesting book. Sorry. There is an interesting book, New Theory of Discriminant Analysis. He uses 8 linear discriminant function to see which one is better. So the author points out, so sorry, I think I'm just keep on sleeping. I think the wrong button. That because there are small differences between Fisher LDF and other LDF, we should no longer use iris data as the evaluation data, because whatever you do, you get the same answer. So it didn't give any insight. So he has to dig out something else. And why does it happen? Is because the test multivariate normality is well ingrained in it. So the data itself speaks for it, that it is a normal and it is optimal in the Fisher. So how am I doing time-wise? So some concluding remarks. So because this is the 60th death day of R.F. Fisher or the year, because I have this collection and people don't believe in dermatoglyphics anymore, statistical dermatoglyphy. So I thought I must put it somewhere as a tribute to him. So this is, I also work in image analysis. So I took a section. So this is one of his thumbprint. So there is some image analysis of it, and just as a tribute to him. So it is used in a spatial analysis book by Kanti and Mardia, Wiley, fingerprint section. So this is the section, what you saw there, a small section, and this has been analyzed. So there is a more in it that those who know spatial statistics, that because of periodicity, the semi-variogram gives the clear idea of what's going on mathematically. So now I take to R.F. Fisher and Darcy Thompson. So he is another of my role model, and because I've worked in shape analysis quite a lot on patterns. So Darcy Thompson, as you know, most of you perhaps, pioneer of shape analysis. His book, Growth and Form, about a few years ago was 100 years. And more details, we have used quite a lot of his work and his ideas in another shape book. So I'm just saying that these books are because of the pioneers. I think these books, why they come is to spread the message, I think, to bring it to the community. So that's the principle. It's not otherwise there will. So this is the letter I dug out from Dundee. His various things are there. So he wrote so I can't find what Darcy wrote to R.F. Fisher, but I could find what R.F. Fisher wrote to Darcy. So he talked about one of the student about Miss Walker, which he wanted to join or as a research assistant. So he says, I quite like to have working here, attending the age problem of fishes as far as it can be approached on existing data. So then this letter continues, a long letter. I've just taken the excerpt. Then he shows, I'm very anxious for this region to see adequate technique developed in such subject as animal genetics and animal nutrition, and also in medical experimentation in all of which lines. Now the peculiar, very important part of Fisher, whatever he did, he threw his heart and soul into it. So I should like to be able to give advice rather than more definite than merely to point to the practice of agriculture field trials. So that's his commitment. Whatever he did was such a strong sense of commitment. However, sadly, nothing happened. I think the student did something different. So otherwise, we would be talking more about shape analysis today as well. I think the third topic. So concluding remarks. From many areas, Fisher had pioneered. So his spherical distribution leading to statistics of manifold, he warned. I think that paper was great warning to these statisticians who like only linear statistics. Using for the data on manifold is erroneous. More details again in another book. So see how much he has inspired. So his linear discriminant function leading to statistical learning and turn to unsupervised learning. So I have my multivariate book, which I wrote in '79, and just now it has gone to the manuscript has gone to Wiley for processing. So there are more details because at that time, in 1979, we didn't have idea that the way the subject takes over, the computer science will play such a fundamental role. We didn't have this. So the other area which I would have liked to continue, except for the time limit and boring you to death. So his exact sample development leading now to simulation approaches, but they are very clever ideas, the way he did distribution of correlation coefficient, multiple correlation for discriminant coefficients. So many, now, of course, with all the changes taken place rightly, that you can simulate and you can get either bootstrap or you do the various ways. So George Bernard wrote in Fisher obituary, to attempt in a few words to assess the contribution made to a subject by one largely responsible for its creation, I think it's very important, I think, would be futile. Now this is my twist to it. I hope you agree. To sum it, it will not be an exaggeration to say that R. A. Fisher is the Albert Einstein of statistics. That's what I feel, that what he covered, still everything what he did, it has a continuation. I think, and the legacy is so much. And I've seen that how much it has gone beyond. So now, my famous last slide in all the talks, underlying principle of Fisher or general statistics, and I wrote a paper in significance, holistic statistics, where I define this. So this image is based on the parable of 6 blind men. An elephant is used in Jain logic to illustrate its holistic principle called anekandvad. The truth is multidimensional, and I think he followed this throughout this truth, that he went into various different way to search when data is there, what is the truth, science is there, what is the truth. And that's and folks, and many thanks for listening. And
I'd just like to thank Kanti for an extremely entertaining lecture, even for people like myself, who are rather statistically amateurs. I'm Brian Charlesworth, by the way. I'm the chair of the Fisher Memorial Trust, and I'm an evolutionary geneticist, not a statistician. We have a tradition in the Trust to present the lecturer with a silver bowl with their name engraved, and I have great pleasure in presenting this to Kanti.
Am I supposed to open it now?
You're welcome to open and have a look and check that it's genuine silver.
So this is the key part. So, boy,